Okay, Friday of week 2, halfway there. We've had some amazing lectures. He's going to finish us up this morning with his third lecture. Go for it, please.
Okay, thank you, Jeff. Okay, so yeah, 2 weeks in. I've shared, Jeff, I think I shared these lecture notes with you. Hopefully you can transmit them to the students. So here, lecture 3, I didn't quite end lecture 2, but that's okay. I think it'll be a good starter for lecture 3. So today, this is what I hope to get through. I'll first start off by reintroducing to you the non-hydrostatic quasi-geostrophic equations. I know that we went through a bit of a derivation and unified QG theory. So let's get grounded. We'll get grounded again with the equations. And then pretty much today's lecture, I'm just going to work through what we know from analyzing them, and simulating them, okay, and then assess how they're doing with through our collaborations with our experimental colleagues. Okay, so, and again, please feel free, active bunch, so stop and ask questions. Okay, so here they are again. Okay, so just doing a tour again. So when we derive these equations, we know we in the low Rossby number limit, the principal balance that we were seeing was geostrophic balance. I haven't wrote geostrophy down here, but that essentially gives pressure is the stream function, the velocity stream function, and then we can see that our velocity field can be decomposed in this way, where the horizontal components of the velocity field are given by the pressure. So this is a reduction. Typically we have a quadratic relation between pressure and the vertical velocity. So leading order horizontally incompressible. I should say that if you're thinking about 3D incompressibility, we know that we have this at leading order for geostrophy. Okay, that comes from geostrophic balance and incompressibility. So, but higher order, when we're looking at the remainder of the ageostrophic field, okay, once we've determined the vertical velocity, we can close and, so we can have 3D incompressibility in this manner. Okay, so, and then we learned actually when we were looking at balances that in the mean temperature and the temperature fluctuations, I've written it down here. This will really, Ekman to 1/3 is really going to be a Rossby number here, but they're separated. The fluctuations about the mean are small. So if you recall, here are the equations, again, that represent the non-hydrostatic QG equations and the ones that we're going to look at to study rotating convection, rotating really Bernard convection to be precise. We got the evolution of vertical vorticity, vertical velocity, the temperature fluctuation, and then the mean temperature field. Okay, so, and I ended last lecture by saying talking about some of the properties that some distinguishes it from standard classical stratified QG. Okay, and some things are similar. Okay, so we know that this is one. We learned then when we're doing the force balances that the velocity fields are isotropic. So if you recall when we were doing the QG theory and we had these two tunable parameters, the Rossby number and the aspect ratio, we saw that for this regime where we're talking about the convective regime where the aspect ratio becomes a Rossby number, that becomes actually right here, times u. It tells you that this thing in this theory, when we were doing QG, that all the velocity fields are indeed isotropic. One of the hallmarks of QG we found out was that no vertical nonlinear advection we saw there. And then also one of the things that gave a reduction was the fact because of this anisotropy, columnar anisotropy, we saw that vertical diffusion was subdominant. So primarily in these equations, they are it's horizontal dissipation that acts on the fluid. And the only place we see a vertical diffusion term that we saw last lecture was this in the mean temperature rate, the mean temperature field, and we motivated that. It's convection. So we know that we need a flux feedback to indeed change, to feedback and mix the fluid and change the background temperature, gradient there, yeah? And in the first lecture, we talked about inertial waves. The thing that survives here in terms of the spectrum of inertial waves, okay? So we talked about slow and fast, and I don't know, I mentioned this last lecture. So we retain these slow, almost balanced inertial waves. So these are the ones that are propagating horizontally with their phase velocity, but then energy is being transported above. And this is what we have for the dispersion relation. So you can see on the bottom, typically, this is the non-dimensional one here. At the bottom, you would normally have a total wave number derivative. And because we've got small vertical wave numbers, that's gone there. Okay, so waves are in here. From these, the inertial waves are in here. And if you actually made this a stable layer, it would be slow inertial gravity waves. But we're able to sort of flip the sign, and we can also do convection in the problem. Okay. And just to touch off again, we saw that, in terms of looking at the inviscid or the ideal properties of these equations, that we conserved energy. Okay, so you can quickly see that if you no forcing, so get rid of the buoyancy term here and all the dissipation terms, and you should be able to show that this volume averaged energy in this way is conserved. But unlike QG, the classical QG or stable layer QG, entropy is not conserved. So I didn't really define entropy in this thing. So, but if you do the volume average entropy for typical QG would just be this, in QG will be the potential vorticity, what they have. Well, I'm going to write like this. But in this case, if you're doing the vorticity squared, you would see if you try to figure out write it down. So that's just the vorticity squared that I've written here. I haven't written down here. You find that this thing destroys the conservation of entropy. So if you do that and you try to plug that in and try to show that this was a conserved quantity, you would find out. So you can do this by hitting the top equation here by zeta, and then hitting the vertical velocity equation by the Laplacian squared of zeta, integrate, and then you'll find out there's a nonlinear term that survives, and then that means you get pretty strong vortex stretching in this problem, unlike the classical QG. Okay, so, and we'll hold on to this for the talk. Entropy is not conserved. First lecture, we made this argument that if you've got two conserved quantities, okay, that's sort of a necessary condition for seeing an inverse cascade. Okay, question mark here. So stay tuned as we go through some of the solutions. Do I have a big sigh here? Typo. Sorry. Yes, Brad.
What's the expression for the total energy?
Oh, this one here? What I've written here? This is a kinetic energy. Oh, you would have to add in the theta term. So if you hit, you hit this by W, hit this by theta, yeah, and add it together, and you would get there will be a no, that's right. You'll get the temperature term here. You would see that this term, and this term, you'll be able to put together in a perfect derivative, and then you'll be able to find out the potential part. But it's convection. The reason I haven't written down is you add it together. That's not positive definite. In QG it is because of the dz by dt bar. Yeah, you're used to seeing that as positive in a stable layer. It's negative. So when you look at kinetic plus potential, if you write it that way, you'll see that it's not a positive definite quantity. Okay, so not particularly useful in that. Okay. Yeah. Yeah, so this is when you do the asymptotic. So we end up seeing, you see because of the stretching or the columnar stretching, z is a slow derivative. Okay, w is still order 1. Okay, so ag has to be Rossby number. Okay, in that. So okay, but yeah, but if you're talking about complete incompressibility, you need both in this way. Okay. Okay, so those are equation. So hopefully we're grounded, and we're going to start taking a tour through them and how we use solutions to these things. So, so just another comment, so we talked about, I was doing linear theory, and we were doing it from the point of view from the complete equation set, Navier-Stokes equations. But these equations, we showed that there was an asymptote. They're embedded in these equations. Okay, if you do the linear stability theory for Rayleigh-Benard convection that we'll look at in more depth as we go through, you actually capture the asymptotic curve for steady and oscillatory convection. I showed these in the last lecture, and I also made this point here that if you put the numbers in, we saw that this reduced Rayleigh number. We saw that this reduced Rayleigh number was really, it turned out with the scaling was really this Rayleigh number times Ekman to the 4/3. Okay, and if you put some geophysical numbers in here, I pointed out. So if you're doing the Earth, you do 10 to the minus 15 for the Ekman number, and I put here, you got 100. I've put it up here. You can see that you're on the order of Rayleigh 10 to the 22, which is sort of you believe this is putting you in the ballpark of GAFD in the objects that we're looking at. Let me say a word about the validity of the model. So it's an asymptotic model. When does it break down? Or so we can put an upper bound. We can put an upper bound on that. So if I go back, the upper bound is that you have to retain geostrophy. Yeah. So I don't want any of these terms rising to this leading order pointwise balance, which I haven't written down. So on top of these equations, we know that we have this constraint that we can do it this way. We have geostrophy. Yeah. So pointwise, this is always going to be the dominant balance, and this is the dynamic balance, the QG balance that follows from that. So we don't want things rising. So this actually gives an upper bound on this Rayleigh number here. How large can we make that before that term can rise and enter this balance, thereby destroying geostrophy. Okay, so and that's just the back of the envelope. If it rises, it shows you that this reduced Rayleigh number is bounded by this Ekman number to the minus 130. It's got to be so for this theory to be to hold. Okay, we're always going to presume that this is an upper bound on the Rayleigh number. Okay, and if you put that in here, if I put the Earth parameter in there, that's 10 to the 5 for this thing. Okay, so it gives you a range. So that's pretty large. So we've got 100 up here, but it shows that that's a large range. Of course, if you lower the Ekman number and you're getting towards the labs, if you keep the Ekman number fixed and you keep increasing the force in, the heating, you're going to break that balance. Okay, you're going to break that balance. The Rossby number is going to get big. You're going to break this, and this model no longer becomes valid. Okay, but the way it's set up now, we can't get out of it. Okay, we're embedded in this regime. Okay, and you'll see that as we go through. Okay, so let's start taking a look at some of the solutions here. So it's pretty rare that you can get what I call some exact solutions to nonlinear PDEs, and we actually find that this system, or this reduced set of equations, of non-hydrostatic QG equations, actually admit what we call a class of single mode solutions. Okay, so I'll just share. This is very straightforward to show. So if you pose, I've got this pose, so you can pose an ansatz here of a separable solution for all the variables, but here's one for W. Okay, and we can see that this H is going to satisfy this what we call a planform equation. That's a separability equation for separability. K perp is going to be the wave number, Okay, so we learned from linear stability in the upright case, there's, we can have a whole ring of unstable wave numbers for a given magnitude. But you can have, satisfying this planform, things that tessellate the plane. You can have a class of solutions that tessellate the plane like this. Hexagons, I haven't written rolls on there, or rectangular type patterns. If you put that in to these equations, you learn that, because of this criteria, this criteria here, all the horizontal advection terms are just zero for this solution. Okay, so identically zero. The only place where nonlinearity persists is in this convective feedback. Okay, so if we do that, okay, so we can get rid of those terms, and then you'll have that. Okay, so this is essentially a quasi-linear set of PDEs, and this is if you solve this, you're actually just solving for the vertical structure of that. So we presume that we know the horizontal structure, and now we can play with tuning the Rayleigh number up, and then we can start looking at what kind of solutions are, what kind of structure of the solutions that happen here. So I can do it. You can do it for both oscillatory and steady. I'm just going to talk about steady here in terms of that. Let's collapse the system. So it shows you the simplification to the system. Once we do that, you can take that, drop the time-dependent terms, and you get this. These are the equations that describe the vertical profiles of the equation. So it's really second order. Okay, a second order nonlinear problem. So the nonlinearity is embedded in here. So you can see this is the mean temperature gradient. Okay, you can see how we've related it. There's this non-dimensional number here, the Nusselt number. That's, so that's the efficiency of the heat transport. So that's just telling you how much heat is being carried by convection versus conduction, normalized. Okay, and we know for the really Bernard case, which I put in yesterday, the temperature drop, the non-dimensional temperature drop is -1. So if we integrate that, we can actually get an expression for the Nusselt number. This is a nonlinear eigenvalue problem. So if you try to solve it with the boundary conditions, I didn't write them here. So impenetrability. So I talked about some of the properties of the PDE equation at the beginning, only having 2 derivatives in the vertical. So all we had to do is impose impenetrability. So we can solve, we can just go ahead and actually solve, straightforward this nonlinear eigenvalue problem. Okay, so I'll show you some solutions. Okay, but prior to doing that, I'd like to, these are, we have, this set of PDEs. Okay, we believe that the correct asymptotic PDEs. So these, in this limit of low Rossby number or low Ekman number, these are solutions. These are exact solutions, okay, to, rapidly rotating Rayleigh-Bernard convection in this. And because of that, if you actually try to solve these and put them in and sort of see if they persist, they're unstable. Yeah, so these are sort of exact unstable solutions to the Rayleigh-Bernard problem. And I just have this schematic here. So they actually form their true solutions of phase space from a dynamical systems point of view. So they provide a structure, within phase space where how, your real solutions will propagate through this phase space. So actually knowing something about these solutions is actually very helpful. And we'll see this throughout the talk. Actually, we'll be reverting back to these single mode solutions to learn what we see in the fully nonlinear solutions. And we will use that to help us, okay? So, we got a pretty simple set of equations here. I mean, if you look at, some of you may look at shear flow, when they're doing shear flow and they have, exact coherent structures, they play the same game there, where they try to find, these fully nonlinear steady solutions, or maybe simple oscillatory solutions to that. It's a lot harder than this in terms of what you have to do, and they kind of use that to sort of as a guidance to try to sort of understand what the turbulent flow in that fluid here. So these are quite useful from that point of view. Okay, so just few solutions. Okay, so it's not unsurprising when you solve these things. So I'm just going to go through a few plots here. So here I'm just varying or increasing the reduced Rayleigh number. So I've gone up to 1,000 here. And you just see these things are just sinusoidal vertical structures, you know, so this is not too surprising. I've put both steady and oscillatory. Oscillatory is in solid and steady is in here. So in terms of the vertical, I've got A here because it came from another paper, but in terms of the vertical velocity, you know, it's sinusoidal. I didn't plot this here, but if we'll see this, we'll need this knowledge of this later. But if we do the temperature field, the mean temperature fluctuation, the temperature fluctuation, it kind of looks like what we expect from Rayleigh-Benard convection. So actually, this is Z up here, and this is theta. So as we increase this thing, we see it develops the characteristic double bumps as we go through. And if you track the mean temperature profile, from this, you actually see, so this is the only nonlinearity in the problem is, you know, the feedback. This is a mode interacting with itself. This is the feedback, and of course, it's doing what you expect for convection. We start off with a linear profile going across here, and as we increase the Rayleigh number, you can see this thing is approaching an isothermal interior. Okay, and we can actually figure out how it approaches this isothermality in terms of in the interior. The single mode equations tell us that. If I go back a few here, so this has got to be, you know, it's a very simple calculation if you do this. You know, the nonlinearity is embedded here. This has to remain order 1. If you put this in here, you see Rayleigh number times the Nusselt number. To remain order 1, W squared has to go like Rayleigh number times the Nusselt number. So W is the square root of that. Put it back in, and then you'll see that, you know, dz by dt bar has to approach the isothermal core with that scaling, and yeah, it's there. If we do, so we're just getting used to these solutions. If we actually do an oscillatory type solution from an oscillatory onset, these equations show that this thing is just the oscillation of the pattern is just it saturates in this way. Okay, and finally, we'll hold on to this result as well, that, you know, you can look at the efficiency of heat transport as you go across the layer, and K's Nusselt number here, and it's monotonically increasing. And if you're not going to do this one, but if you work with the equations, you can actually show that it scales at large Rayleigh number in this way, you know, in terms of the, you know, thing, Rayleigh number log Rayleigh number for this. So that's a way of characterizing. This is a way of just characterizing the single mode solutions here. Okay, so those are the structure of single mode solutions that they kind of provide the skeleton for space. Yes. Well, so yeah, I mean, it's really a function of the nonlinearity that the oscillations, you know, you're asking whether why they saturate, yeah? Well, yeah, we know that shouldn't keep going, okay, because we know that's, in terms of if it keeps going, we know that we're looking at slow inertial waves. We don't want to keep going. So it's just a function of what the, you know, solving the equations have told us. It tells us they grow and they saturate. You know, it could have gone the other way, but it's told us that's just, you know, the nonlinearity in that. Well, the amplitudes still keep increasing, you know, so it's a nonlinear problem. It's just satisfying itself in this way where this thing saturates, yeah. Well, I missed that there is a K, there's a Nusselt number in here as well, correction to this, but yes, slightly, but this is the scaling. this is yeah. So yeah. So it's got a small. Well, it's yeah. As this goes, as this is increasing, yeah, it should be bending up just slightly greater than 1. Okay. The analysis tells you if you just get the first order correction to this, it tells you it's going like this. Okay. Okay, so let's go. So those are the single mode. Those are the single mode solutions. Okay, so now we're going to go and just take a tour of what the fully nonlinear solutions give us to this. Okay, so we're going to solve. We want to solve these equations, and to do that, we're going to have the really Bernard setup. So it's just going to be we're looking at plane parallel model with bounded plates at the top and bottom, separated by a non-dimensional distance of 1, and we're going to have periodic sidewalls. So it's periodic layer, and this is there's still an effort to solve these things. So we have an algorithm. It's a standard because we're periodic in the horizontal. We can use a Fourier decomposition. We're bounded in the vertical, and we're going to develop boundary layer dynamics. So we choose a set of spectral representation that puts the resources or the resolution where we want, and it's a fast so it is it's a pseudospectral code. So nonlinearities are treated explicitly. You guys had a talk by Jeff Owishi, I guess, 3 Dedulus talks. So I mean, the algorithm is pretty much the underlying foundation by which Dedulus solves its nonlinear PDE. It's the same structure here. So I'm sure Jeff talked about the paper there. Okay, so going to take a tour through some of the solutions that we observe from this equation. So in solving these equations, we perform a survey of parameter space. So we'll do a suite of simulations where we're using, so sigma here, we're using Prandtl number on the bottom, and we're scanning up with the reduced Rayleigh number on the vertical axis here. And we find, and I'm going to explain some of these in turn, we actually find a successive class of complexity in the solutions observed in the layer, and we kind of map them out. Okay, so this is the flow morphology in this. Okay, and I'll say a little later that in the laboratory experiments, we'll see that it's pretty hard to get into this regime and sustain yourself in this regime where you can actually get enough of a range to actually try to understand these flow morphology. So in some sense, these are sort of complementary. This is a complementary effort that helps the experimentalists understand some of the solutions they have. So there are 4 types of flow morphologies we see as we increase the Rayleigh number. Cells, I'll talk about the convective Taylor columns, plumes, and then geostrophic turbulence as a final state for these solutions. And we can see how they're mapped out with the Prandtl number here. So I won't say so much. I mean, cells, we have the cells, I mean, these are just like the single mode solutions that I was showing. You look at the horizontal tessellated just above onset, in this case, you get something that looks like a square-like pattern. They're not steady like the single mode solution, they're unstable. So if you actually look at a movie of these and you look them down on top of them, there's an instability in rotating convection called the Cooper's laws, where if you have a roll, it kind of loses stability to another roll at another angle. So these, you'll see these things will jiggle as you do that. But largely, you should think about this as sort of the pure single mode solution that we saw from the reduction of those very single wave number or tessellated solutions across the plane. Yes, Peter. Yeah. So if you look down on this, you'll see a regularish pattern. Okay. Ish. Yeah. Ish. Yeah. So the ish means that they're not steady. Okay. There's a little dynamics. There's a little dynamics to it. No, you can. In this case, you probably can see some. Non-uniformity, but really, for this, they're quite regular in that sense, and they just, you can see some oscillatory motion, some jiggling around here. Okay, so as we increase, so you saw as we increase the radiant number, we're building, the fluid is mixing and we're building, it's trying to build an isothermal interior, and it's trying to build a thermal boundary layers, okay? So as you increase this, you get something quite, striking happens to the fluid flow. We get, we get a pattern that looks like this. We call them convective Taylor columns. So here again, I think Freddie had mentioned this in his talk. We're just looking at the thermal anomaly. So as you go across the layer, we've subtracted out the background mean. Okay, so every layer you're just looking at every layer depth, you're just looking at the fluctuations about the mean value of temperature at that layer. So we get these convective Taylor columns, and how do these occur? Okay, so it turns out, so if you look at these, so we're going to see these are columns of warm and cold anomaly. So warm anomaly is where fluid is being carried up, and a cold anomaly is where fluid is being carried down. We see this in all fields, the vertical velocity field, the vertical vorticity field. We may look a little different because it's got a cosine profile, but we see these columnar structures extending from boundary to boundary. Okay, and you may notice, I'll say some more about this in a second, this is a visualization, so you can't get the entire thing. We'll see that they actually have oppositely signed anomalies around the cores, okay? So they're shielded, okay? And we'll say some more about that in a second. So how do they occur? Well, it's really an instability of the thermal boundary layer, okay? So we know that even in non-rotating convection, if you drive the fluid, and eventually the thermal boundary layer, which has an unstable gradient, it becomes unstable again, and you develop sort of a blob instability. Okay, in this case, we get an unstable boundary layer in the rapidly rotating limit, and we get this is what happens when it happens. You get fluid descending from the boundary layers, from two boundary layers, and what actually happens is that they actually synchronize. Okay, so you get a boundary layer instability here, and it becomes a sort of a zone of high propensity to sort of hook up with a boundary layer instability at the bottom, and they actually form these what we call convective Taylor columns. Okay, the fluid loves this because these are just direct heat conduits. Okay, going from the bottom to the top. Okay, so if the purpose of the fluid is to transport, heat efficiently from top to bottom, this is a structure that it actually it would like to form. So, what is your color scale? Yeah. So the color scale. Yeah. So we're looking at heat anomaly. Okay. So the mean, we're subtracting off the mean temperature profile. Okay. This is a total temperature. Okay. So the sign in this sign, blue is cold, so colder than its mean. Okay. And red is warmer than its mean. Okay. This, oh, sorry. Yeah. Oh, so I should have put up thank you. I should have put up the really Bernard thing that I had last lecture. So, yeah. So, no, this yeah, is an appropriate and good question. So, so we've got a layer, an infinite layer that is rotating. Okay. So, and the top is being held at temperature. Bottom is non-dimensionalized temperature 1. The vertical velocity in the plates is equal to 0. So you're actually looking at a perspective view here. Yeah. So if this is a layer of fluid here, we're seeing a set of columns that are extending from the bottom plate to the hot plate, and you're in the rotating. You are in the rotating frame of the fluid. Oh, so I'm plotting the temperature. This is thermal anomaly. Okay, the temperature.
So the color scale is temperature. What is the actual surface?
So these are iso. You see, these are just iso surfaces of the thermal anomaly. Okay, so yes. So yes. So So if you're looking at, well, I've got a color, I've got a color plot, which goes from cold, which is blue. Yeah. So, oh, it's a surface of constant thermal anomaly. So choose a value, okay, and it's picking that, it's picking that value for the surface. So it's a level contour of the isosurfaces. Okay, so, and the software. I think the software here is using either Vapor, which is software from NCAR, which you put a color scale in, okay, and then you can vary the opacity, okay, so you can see through the fluid for certain iso contours that you don't want to pick out, and you vary it until you latch on to this. Yes. Yeah, hold on to that. Yeah, we'll see that in a second. Okay, so that's a good question. So I should put that. So yeah, so it's really, perhaps on initial conditions. If you look at the equations that I put down, there is a symmetry that I should have mentioned. So if you look at the symmetry of these non-hydrostatic QG equations, they actually have a reflection symmetry. I should write this way. You can show that the solutions are invariant under this reflection symmetry. Yeah. So y. So choose. Yeah. So choose if x. It doesn't matter here. Choose x this way on the plate, y this way on the plate, and z is going up. Yeah. So you can do it the other way with x as well. But there's this reflection symmetry, which is, we're in the rapidly rotating limit, which is supposed to be have-handedness, yeah. But yet we've got this reflection symmetry. So in this limit of low Rossby number, it restores this symmetry. Okay, and if you actually look at the action on the fluid variables, so if I look at what's the psi or the vorticities associated with this W, the thermal anomaly, and the mean temperature in this way. You'll find that with that symmetry, it maps to, so it changes the sign of psi, or it will change the sign of the vorticity. Okay, it will change the sign of the vertical velocity, change the sign of the temperature fluctuation, but keep the sign of the mean temperature. So your question is that, these should be equally likely, okay, when you do this, but this is just a consequence of the nonlinear, the seed field you put in. I could very well just take this solution, okay, apply that, and you'll get the same, you'll get the same solution flipped, yeah? So it's just the way the nonlinearity has, but they are equal propensity. This is true in the QG equation. So this is why you have this symmetry between cyclonic and anticyclonic as a Rossby number gets pretty low, and you've got to get to finite Rossby number before you kind of break this. So we're in this finite Rossby number limit here. So it is a boundary layer instability, and this is where we can actually use single mode theory again to guide us that this is indeed the case. So if you go back, we can go back to the single mode. Okay, we can actually look at the nonlinear temperature profiles that it's generating, and then we can actually do a boundary layer analysis. Okay, so we can actually, what we do here, we actually just rescale those equations into the boundary layer, almost like a semi-infinite plane, and we just do the stability problem. Okay, so on this left-hand side, we're just seeing what this curve Nusselt number is curving up now. So this is right there. So this Nusselt number, this is what you would get by solving the single mode solutions, Nusselt versus Rayleigh. But we can also, when we recast this problem, we can recast it by scaling everything with regard to the Nusselt number, and we can get out the instability of the boundary layer at a critical. We can get a critical Nusselt number where the boundary layer becomes unstable. Okay, so as you increase the temperature, there's a critical rating number where the boundary layer becomes unstable. And if you go up again, the difference between those two things is when it becomes unstable. Okay, so for this, this is how supercritical you are in terms of the boundary. This is a realizable solution. If you go back, this is when the boundary layer became unstable to this this situation where it would generate these convective Taylor columns. Okay, and the curve on the right kind of shows you the boundary layer eigenfunctions. So going back to Freddie's comment, so let's look at what this looks like. So this is, if you're looking, we're going to do a simulation at this 40. So we kind of start with the square pattern here and let it go. Yeah. So this is you can think about this as being a single mode solution, which is unstable. Okay. And we're just going to let it go. Okay. And see what it does. Yeah, this is, sorry, I'm clicking a rendition of movies over the years here. So this is indeed, this is going to be temperature again, just we're using a different color scale again, but sort of the same, we're using the same thing, we're going to look through the fluid and, plot isosurfaces on it. So there we go. So the boundary layer is unstable, so you can see what happens. You will see that you immediately descends into these convective Taylor columns, and if you wait long enough, you can see they start to develop. They'll start to develop these shields. Now, if I take slices throughout the whole layer, this is just because of the color bar, the color scale we're using. These shields go top to bottom. Okay, it's really because if we're doing a contour of temperature, we've got more intensity at the top, so there's a tendency to see what the shields at the top, and with the color scales, we can't see the shields in the interior. So they're dynamic in that if you're looking at them, they're actually slowly advecting. Okay, and the shielding actually, they're very weakly interacting. If you follow one of these things, they pretty much are surviving the life of the simulation. So they're really weakly, because they're shielded, they're weakly interacting columns. And they play.
Some infinite time limit to eventually reach some kind of steady state.
Well, so there are solutions where these things, there are solutions that you see in labs where they actually can crystallize onto a lattice, okay? But these are periodic, so you've got to have a perfect state, so they're always jiggly. So I don't think you'll see them here, but you can, they have been seen in the lab where they form these crystallized hexagon. Yeah, they're like, so they're always dynamic here. They won't evolve to a crystalline state, but that is a potential solution to the problem. Heat, we're putting heat through. It's an unstable layer, yeah. So it's just, is there an unbalanced source of unbalanced motions in this? Well, there's turbulent, there's turbulent agitation between these things that we don't see, okay. And there are, they're probably connected through. Well, yeah. I don't know where. Well, not much to say here. I think that's just what we're seeing here, But there's turbulent agitation. There's probably you'll see they're not quite, as they get close to each other, they're not quite shielded. So there are a small interaction, but you can see they're not, it's not like normal vortex interactions where you have heavy mergers. Okay, they're just sort of, weakly pushing each other around, and there's probably a background field, gradient field that's sort of moving them around. Okay, Adrian. No, so this was my point here. Question here. It's kind of hard to see because of the intent. If you actually look at if you took a slice of this of that, you will see, you will see this kind of profile in the temperature anomaly. Yeah, you'll see that. Okay, so when you put a color scale on that, you can't, you're going to see. If I try to do hair, I will saturate the whole field, and that would be hard to see. So I'm picking, so primarily it really focuses on, it's picked up the intensity hair, and as we go down, the color table is bleeding out the shields going on. But we'll get to this in a second, so we can look at that. Yes. Yeah, it's actually the thermal boundary layer. Yeah, so it's the thermal boundary layer is getting getting thinner and thinner, okay? And that sort of, that sets the size, that says the size of the columns, okay? So it's a good, we'll hold on to that as well. It sets the size of the columns and the space for them to form, yeah? So, yes?
I think you find Ross's radius.
Well, in the original way we derived the fluid, there was a Rossby deformation radius. It's an unstable layer. So NH over F defined this way. Really, this is being set by the thermal boundary. The thermal boundary layer. The thermal boundary layer is getting thinner and thinner. Okay, and we're going to see that happening. Okay. Okay, so we had a question about the structure of this. Well, first, if you take so you can actually find, you can just take numerically, you can go in and look at a cross section of these plumes, and you can see what the radial profile is. So I'll just hit that. I'll just hit that here, and you see. So this is sort of an averaged radial average of the plumes, actually. So it's easy. You can actually do this. So if you take because these are the sort of the dominant structures in the plane, if I take a slice in that and just do the autocorrelation, how, just shift them in both directions and look at how the fluid is coherent. It actually draws out, the autocorrelation function actually draws out the shape of the plume. Okay, so you can find it by doing it numerically, but what we see in every one of these structures, whether it be the velocity field, the vorticity field, or the temperature anomaly field, we see a core, so make it positive. So a large amplitude core, and then this is where it cuts through zero, and then you can see these shields. You can see the shielding on the layers. So that happens at every layer. So if you do this, you'll find this happening at every layer depth in the fluid. So that's showing that the shields are throughout, different strengths, but they are throughout. And if you actually take this for the vorticity and you work out its circulation, it's approximately zero. Okay, so these are so very very weakly interactions. So they are strongly shielded. Okay, so in fact you find that in all the things, the thermal anomaly field and the vertical velocity field. So even they contain their mass. So they're very weakly interacting particles of the flow, and they just like what they're there for. They're very much like to, they're there to sort of conduit heat top to bottom. Okay, so in this paper with a former student, David Nees, we kind of went through this autocorrelations and we're showing the experimentalists how to do this. If you've got a layer of fluid and you can take PIV measurements, okay, and do the same thing, you can potentially do this. And Bob Becky actually did this. This is a courtesy result. So he kind of, in one of his lab experiments, he laid in the field, his field, convecting field with particles, and he did this and picked up the structure of these convective Taylor columns in this way. And you can see this. So here's an actual experiment. This was done by Sakai back in the 90s. So he's got really Bernard convection. He's running at a pretty large Ekman number. It's in water, and he's got these temperature sensitive particles in the flow. Okay, and so this is again, so if you look on top, this is the top layer here. So this is like the thermal anomaly here. So you can see evidence of these sort of convective Taylor columns in the flow. Of course, this is not anomaly, this is a total temperature. So you can see it's pretty much guided by the warm boundaries and the cold boundaries. You can pick out the hot and cold columns here, okay? And you can see that these things do have, I failed to say this, they have vortical structure. They have, so we saw cold, different anomalies. So you can get vortical cores that are, if you've got a downwelling plume here, it'll be cyclonic at the top. And then if you go down to the bottom, you'll see it spins down and it becomes anticyclonic at the bottom for the vortical structure of this. Yes. Yeah. It's same. So we'll call this a convective Taylor column regime. Yeah. they're not interacting. Yeah, okay. Well, again, this is, we're in the limit. I will say caveat that, the Rossby number is, or the Ekman number is pretty high here, okay? But, you can see, you can see that these structures in the main point here, they're spanning top to bottom, okay? So again, we can model these. So if we go back to the single mode equations and try to sort of see how do we can we capture this in the profile. So now we can't just tessellate the plane. So what we do here is that we model this, and you can't just choose. Also, you would think that if you're looking for a representation of a column, you would probably think about in cylindrical coordinates. You would think about just having a Bessel function. You can't use Bessel functions. Actually, if you actually do that, they have the wrong physical properties. You integrate the circulation, it becomes infinite, unless you truncate it. So we model them with, extending that. We model them with a Hankel function here, and where K perp becomes a complex. So we can actually, using that, we can actually get the thing to, we can get the envelope to decay. And the single mode equations look much like the tessellated part, where we can model a structure of this type, a convective Taylor column with this structure in the vertical decay, and because of the complex wave number in this way. And we can adjust the density of these things. So there's a variable, the density per unit area. So we can model the heat flux as a number of these columns per unit area. And then we can also have a tunable parameter if there's heat flux due to the turbulent background as well. So it's a similar type equation that we have. It's a nonlinear boundary value problem. And we find that you can actually get a good fit. So we can take, in black is the numerical simulation of the fluid of those equations, and in blue is sort of a best fit profile of the radial structure. And once we have that, we can actually look at how well it's doing compared to the black is the real solution, how well it's doing to compared, it's not perfect, but how well it's doing in the thermal, in the mean temperature gradient. So these are all, so these here are all, they're all vertical profiles. So compared to the actual fit, so not doing so badly here. I should go to the next one. It does. So Y0? This is part of. So that's part of. So good question. So that's just part of making this choice. So Y0 has a log singularity. So it's not perfect, but we can. It's weak. Yeah. It's weak. And then if you actually look at the circulation of this, the log singularity doesn't make the solution unphysical in this way. So, and the next, I think it's the next slide. We actually do some fits. So again, black is the actual mean temperature profile for the best fit, and then there are several things here, but just the blue is doing this with this 0, and then we can actually step in by tuning, saying that doesn't carry the entire heat flux, but there is some turbulence carrying the heat flux. Okay, so that's sort of the single mode, the convective Taylor column, regime. Yes.
The energy of those Taylor columns, that's singular structure, in the sense that the viscosity times entropy of the structure would be finite.
Viscosity times the entropy. These are all fine. They're finite. They're finite in this way. So you're asking if the viscosity goes to 0, does something blow up? Remain constant. We haven't really looked at that, but I would suspect that it probably remains constant in this case. Okay, so but we had, so again, these are dissipative solutions. So sort of, so as we, as we go up, well, the amplitudes are going to going to increase. Viscosity is always in here. Viscosity is always acting to make these, make these columns. So I think I mentioned last lecture that when you're breaking the Taylor parameter constraint, the viscosity is an active ingredient in sort of setting that scale as well. So I think viscosity is always going to remain important. Okay, as you go to more and more non-linearities here. Okay. So this is this regime here. Depending on the Prandtl number, as you increase this, so I said that these Taylor columns are really controlled by the boundary layer depth, yeah? So as you increase the radiant number and your boundary layer is getting thinner and thinner, okay, that's saying that your effective distance between the boundaries in terms of when you're looking at the thermal anomaly or the extent by which particles can fall from one boundary to the other, the distance is getting greater and greater, okay? So what you find as you increase the radiant number, they desynchronize, the boundary layers start to desynchronize in terms of forming these synchronized columns. So we enter this plume state, and this plume state is just saying that what we find in this plume state is that the columns will form, okay, but they're intermittent. You know, they're not able to sort of retain this bond between the top and the bottom. And if you follow a column there, you'll see, you may pick one out and you'll see it breaks, and then it forms, it breaks, and then it forms in this way. Okay, so it breaks in this way, and if you're looking on the top surface, you know, you probably can see that there is, I'm going to come back into a second, there is, you can probably see some large scale phenomena visible on the surface on this, okay? So there's a large scale coherent structure on the surface. One of the things we notice if you're looking at the mean temperature profile, we actually see that rather than approaching an isothermal limit, so we've got this for different Prandtl numbers, as you increase the radiant number, the fluid doesn't mix completely, okay? It grows and it maintains an unstable temperature gradient, okay? And we saw this, we see this actually in early DNS studies, and all what's going on there, because we've broken, you know, these columns are actually mixers now, okay? So, and the shield, and also they've also lost their shielding. So there's a strong vortex interactions going on, and there's very strong lateral mixing, okay? And what happens here is that you can imagine a plume that is a warm plume that's trying to make its way across the layer, okay? It doesn't make it all the way like you do in really Bernard or equal propensity, you know, from top warm and cold plumes, they get mixed out. So there's a propensity to mix out the thermal anomaly at the lower layer, thereby warming it, and a propensity to mix out cool fluid coming out of the upper layer, thereby warming that as well. So it builds an unstable and sustains an unstable temperature gradient. Okay, and you can see that if you take a measurement of the mean temperature at the midplane, you can see when these convective Taylor columns occur, you can see the break. This solid line here is actually what you would get from the like single mode solution. So it's telling you the convective Taylor columns and the cell solutions try to follow this isothermal scaling, where the radiant numbers, the mean temperature is trying to reach isothermality with this exponent, but it eventually breaks once you got into this plume regime, and it starts mixing this way. It sustains this gradient, and you can see that we now saturate the mean temperature in the midlane. Yeah. Well, this is all, I mean, so inertial waves, you mean, versus, no, we have not done that. There are slow inertial waves. There are slow inertial waves. I imagine it is if you can try to do this with the field, but we have not done that, yeah? There are slow inertial waves in this problem. But these are real, I mean, these are all columnar or eddy type, type structures.
Can I think of this flow as an interaction between these two components of the flow, the slow and the fast?
No, well, everything's slow here. So I know that you're saying that, fast inertial waves have been filtered. If you're thinking about fast inertial waves have been filtered out, okay? But you may be able to think of the flow in terms of the interaction of the eddies and slow inertial waves, okay? So I would say it from that point of view. We're used to about in terms of stable air QJ, fast inertial waves and eddies, okay? But in this, so in QG, yeah, because you've got strong stratification, you know, you're bounding, you know, the inertial waves. You bound the inertial, I guess you bound the inertial waves. They're bounded, I guess, in what Anton was showing. There's a lower, you know, you bound them. Yeah. So the inertial waves here, the spectrum of inertial waves here are slow. The fast ones, if you look at the dispersion relations, they in this rendition, they all go off to infinity. Okay, but they're not playing a role. The fast inertial waves are not in here. They're being filtered out, okay? This, yeah, so I explained, so if you go back to the single mode solutions, you can think about those solutions there. You look at the structure of those equations, okay, to retain the nonlinearity in those, the nonlinearity in that equation. So if I say it this way. So we had this sort of dZz of W, and then we had this temperature thing, Rayleigh times dZt bar, okay, times W here. So the convective Taylor columns kind of follow this single mode. They look like they have single mode flavor. And then we had this dZt bar was proportional to the Nusselt number. And we had this W squared over here, yeah? W squared in the bottom. So I'm just picking out pieces of the equation, okay? So if you put that in here, okay, and this has to be order 1 to keep this equation nonlinear, okay? So if you put this thing in here, you've got Rayleigh times Nusselt, okay? So it tells you that, you know, W squared, okay, is going to go like Rayleigh times Nusselt, okay? So W is gonna go like the square root of Rayleigh times W is going to go like the square root of Rayleigh times Nusselt. But if I put this in here, this W squared scaling in here, Nusselt's going to cancel, okay, and you're going to see that dZ by dt bar goes like Rayleigh to the -1, okay. So that's why we see that, okay? So as long as you get sort of something that looks like it's tessellated in the plane or convective Taylor columns, it's going to approach that. As soon as we break that with the plume solutions, it, you know, because of this mixing, okay, that that process no longer holds, okay? So you can see how it goes, and depending on the Prandtl number where it breaks. So it does it, you know, the lower the Prandtl number, the easier it is to sort of break off that scaling, the lower Rayleigh to the -1 scaling. Pardon? Well, so the reason why it breaks off is really yeah. So it's yeah. Yes, yeah. So we want the equation to be non-linear, which they are. Okay, so we know we have to retain non-linearity. So you're just looking at the minimum value that retains, you know, the value that, or the minimum value that retains that in the equation, and that's how you pick up the scaling. Yeah, that's correct. And so, you know, so there's partial desynchronization, and then finally you get to this. Model where the thing is just fully, you know, so the plumes completely lose their shields, you know, they're strong, you know, and most of the coherence is actually of this unstable boundary layers are confined to the top and bottom surfaces, as this rendition is showing. And what we see here is that, you know, we generate this, you know, in this, we call this the geostrophic turbulence regime, excuse me. Let's go back one. We call this the geostrophic turbulence regime. So there's no longer any connectivity between the boundary layer, and it's just a turbulent interior, okay? And you can see here at the top and the bottom that we just have, in the next slide, you can actually see again, you see this large scale circulation in the problem. I'm going to change my color scale on you here, but if you go back and you look at the slice from the thermal anomaly, okay, okay, and the thermal anomaly field, you take a slice, you actually see something like this, where you know, we appear to have generated this vortex dipole with a cold and a warm thermal anomaly, one cyclonic, the other's anti-cyclonic, so in the field, while convection is still going on. So in this case, the convection is essentially, organizing itself and coexisting with this large-scale vortex. And this is just actually evidence. This is an inverse cascade that is happening in the fluid. So at the beginning of the talk, I talked about not having two conserved quantities, so we didn't see this, but it happens. Okay, we see that as the convection is going in this geostrophic regime, it's actually sending energy upscale. Okay, and it forms a condensate, and the condensate reaches Box scale. Okay, in this and then you see this strong, signature in the flow. And we can understand. How do we understand that? It turns out this condensate is actually largely in the energy in this is largely in what we call the barotropic mode or the depth independent mode. Okay, so this is the Z independent mode, okay, is where all the energy, this upscale energy, is being transferred to. Okay, so we can actually decompose so just looking at the horizontal velocity or the stream function that defines the horizontal fields, we can think about decomposing this thing into a barotropic part. This is a depth independent part, and a baroclinic part, which would be the convection. Think of it as the convection, the thing that is overturning. Okay, we can decompose the field that way. Okay, and then we can think about, so this would be the barotropic velocity field with the angular brackets, and everything else will be baroclinic or the convective component. And then you can actually take the vorticity equation and average it. Okay, so, and then you start getting a hint of what's going on in the fluid. So if we do that, we just get the barotropic vorticity equation. So I think Freddie wrote this down in his talk here. So this is the evolution of the barotropic vorticity. Okay, this is a nonlinear term for barotropic, the barotropic field affecting itself. So it's horizontal advection of the barotropic field, and then there's actual forcing due to the underlying convection. Okay, and then dissipation. Okay. So you can integrate these when you're actually integrating the full equations. This actually reaches a balance where the baroclinic forcing meets the balances with the dissipation. Now this is a large scale structure, so these are very large. These are large amplitude structures, but you can see it's it's not a predator prey type model. It's a sort of a symbiotic model between convection and the baroclinic term. So in fact, what we see, so if you look at this equation and ideate that, we have no forcing and no dissipation, it's just the barotropic vorticity equation. So you can imagine that, this equation so this manifold, the depth invariant manifold that is unforced and undamped, okay, has these two pseudo conserved quantities actually. So in that manifold, you see there are two conserved quantities. So you can see there's going to be a tendency to upscale from the first lecture to upscale energy, okay, energy upscale and downscale entropy. And this is what's going on in this picture here. Yeah. So no, they're not small. I mean, these they're not small at all. But when it reaches no. So yeah. So
Are they order one?
These are all they're all. I mean, they're order one in everything's order one. Okay, but when it reaches this, when it reaches a statistical equilibrium, this thing is sort of balancing. You sort of want balancing that thing to bring it into equilibrium. So if you horizontally average this thing. Okay, this and time average, this is 0, this is 0. These two things must balance. You see? Oh, sorry. It does. I mean, at the beginning, yeah. The barotropic vorticity equations I did in lecture 1, was completely. The question should be, why didn't it have a baroclinic component? So you said so. It was out. It was out the problem. So I was saying that you had infinite. In that model, I said the Taylor paradigm was so strong that it gave us infinite depth independence. Okay, so recall one of the ways of breaking the Taylor paradigm theorem. I said depending on your horizontal scale of your plumes or your puck that I did at that time, that's the scale that really sets sets the invariant scale as you go up. Yeah, it's going to be invariant on that scale. And then you can have modulations on top of that. The convection is the modulate, in this problem, in this QG, the convection is the modulation on that scale. So we have these two components. Taylor problem is still operating on these small scales, but the scale of the box is broken with the modulation. Yeah.
Before the balance between the red term
Yeah.
and the black term.
The average balance, yeah.
Isn't it that the blue term, the dominant term, in the sense that if it is 0, it's two large terms that compensate?
Yeah, these two, so yeah, if you do it, so when we do a force balance, you do see this actually. So it's a good question. We actually see that these two terms are pretty large. So yeah, so they're sort of canceling each other. Then you've got the forcing term below, the forcing and dissipation below that. So that is actually indeed correct. So in terms of that. Pardon? Yeah, well, you can think about them that way, a cyclone and an anticyclone in the fluid, they have the same, they'll have the same physics in terms of that. Yeah. Well, you can think about, if sort of layers going around this way, so you can think about one of those being a cyclone and having low pressure interior and relating to high that. So all the aspects of rotating convection is in there. Yeah, yeah. Yeah, so we do have in the papers some force balances that we sort of look at. We look at the full equations, we look at the force balances, but indeed that, you do see, if you actually do a force balance, you do see that these two terms are, well, the material surf advection is pretty large, okay? But when that's independently, so they're sort of canceling each other in this way, but when you add them together, so looking at the full material derivative, all these terms do balance in this way. Okay, so you want that one. So you can do, look at the energetics where you break these things up into. You can look at the energetics of these things in terms of so broken up so this is just looking at you take a horizontal, we take the energetics of this in Fourier space and project onto a magnitude K, so standard energy density plot. You got the black is the barotropic component and the red is the baroclinic. So you can think about this being associated with the large scale vortex, and the other one being associated with the convection. And in the black, the barotropic, you see some key signatures here. So the forcing scale here, you do see, I put some things to guide. It's not exact, this is not an ideal case. The forcing occurs across a range of scale. The dissipation occurs across a range of scale. So we're not really building, in this case, it's really hard to build a true inertial range, but you can kind of see here, signatures of what we will see from 2D dynamics. So you've got a -3, will be the entropy cascade, and I think Hussein was saying this, rather than seeing a -5/3 energy cascade going up, you've got the condensate that has reached, the box size, and energy is being dumped into that. So we see a pretty steep energy signature here. Okay, and these dotted lines, you can actually see these dotted lines here, and here is just a time evolution of showing how that thing is built up. So you can actually see the energy cascading up and down scale. So, and I think Freddie had mentioned this in his talk. This is not it's not a local. It's not this energy cascade is highly non-local. So if you're looking at a transfer plot in 2D, where you're looking at how energy is transferred from one scale to the other, okay, a local cascade will happen, on a vertical line here. Okay, I'll say something about that in a second. But we see that, you see these anything off this is a non-local cascade, and this is where we're seeing that, in building. So this is looking at the transfer, the nonlinear transfer map of the nonlinear term here. What we actually see is, if you come down here, we see energy being extracted at large scales and being dumped into the large scales here. So the fluid is just organizing itself to sort of extract energy, not along wave number to wave number, but this strong non-local jumps in terms of how the fluid is doing this. It's hard to see here, but you can. There's the forcing of the fluid. The energy. This vortex actually changes where the forcing. It changes the injection scale of the fluid and where the injection is being dumped into. It's around here. But in this tail here, this is at the forward cascade of the entropy. If you look at that, you can see. So you can see in this plot, you can see entropy going downscale in a local manner, and energy going upscale in a non-local manner. So this is what this transfer plot is indeed showing. It's got 50 minutes actually, so I'll skip this quick. But we find, if you actually, one of the things in the studies that we find is that this inverse cascade that we thought was in the geostrophic regime, it actually happens once you hit the plume, the plume regime and the turbulent regime. You actually see signatures. You actually see signatures of the inverse in the inverse cascade. And in terms of measuring when the LSV or this inverse cascade happens, it turns out the measure that we find is an empirical measure, is actually the non-dimensional Reynolds number, or the magnitude of the vertical velocity in this. So we're actually able to put a threshold of when we see the development of a large-scale vortex or a pair or not. Okay, and it seems that this line of around 6 seems to be a transitional line of when that happens. We don't understand it, but that's where we put the empirical line where we see these things. Heating is, yeah, so it's just, yeah. Yeah, so you should think about that even for the heat as well. You're putting, that's where these is. Well, that's a complicated question in the sense that you can think about that happening at the beginning, but once this vortex sets up, it does, they're talking to each other. Okay, so it actually does change you can see the injection scale creeping up to larger, because there's a lot of sharing going on here, and so it's not just that scale that stays fixed like you're doing a sort of a standard thing. Yeah, so these things is one of the things. This is a system that is talking to each other, and unlike sort of the ideal studies where you're forcing, delta forcing here and you're watching the thing come up, this is a completely closed system. So as you force, you set up the large scale vortex, but it talks. Okay, so the whole system can arrange itself and talk to each other, and things can then move from that. So it's not that sort of standard classical picture of turbulence. Okay, thanks. Okay, so. Is going. We do, so maybe hopefully I'll get through this in the next 10. So those were the asymptotic equations. Okay, so are we asking, do we see the same things with DNS or even laboratory? Yeah? So we've just gone through some simulations of the asymptotic model, and the idea, yes, if we just repeat the DNS experiments, so this is no approximation. We're just looking at the fully blown, incompressible Navier-Stokes equations, and we're setting an Ekman number, and we're letting this thing go, and we vary the Taylor number. So in collaboration with Stefan Stelmach, we actually use this as a guide. Okay, so we use this as a guide. We picked off a reduced rating number in one of these regimes. So you pick a target. We picked a target in each one of these regimes, and he got to the lowest Ekman numbers he could at that time. Okay, and then pick the Prandtl number, and then go. So, and it happened to me. So at this Ekman number, this is a good map. This is a good map of what you see. So these are all DNS. You saw exactly the same thing. So these equations are faithfully, at least at this Ekman number, low Ekman number, faithfully capturing the these flow morphologies. Okay, and so so this middle part here is just showing, yes, we faithfully capture them in flow morphologies, but there've been some. Do you see these in experiments? There's been a recent experiment by Rudy Koonen's group, where they're seeing, they're seeing evidence of an inverse cascade in the anomaly field, So this is also good news that they're getting there in the lab setting as well. And if we want to extrapolate to, we talked about Jupiter and looked at the poles. Actually, there's been so we saw that from the Juno data. So there's been and this has been faithfully captured in a rotating convection experiment simulation by Kai and others. Complicated what they have, and this was an astrophysical situation, but they put this on a gamma plane. So rather than the beta plane, if you're on the top, rather than having a linear variation that Antoine was talking about in the Coriolis term, you have a quadratic variation. So they did that, and they're able to start reproducing these large scale structures. I didn't have the reference here, but it was on a prior one. There's some recent work by Leah Silgerman and others who are actually using Juno data and actually refer to this model as that these are non-locally driven large-scale vortices by looking at that data. So non-local from the underlying moist convection, as they state here, in terms of driving that. So so the mechanism seems to be, at least that's nice for us to see. The mechanism seems to be there in action in GAFD. So it could be interesting to put this on a gamma plane as well in this extreme limit and see that we can capture these things. In the lab, I should just point out, here are all some of the laboratory experiments that are going on around the globe right now, including those of my collaborator in UCLA. There's this one here by the tall tank experiment by Rudy Koonen's group. And really all of these are, especially this big tank here, 4-meter tank's really been built to try to access the geostrophic turbulence regime, okay? This is hard to do, okay? So just to symbolize why that is, so we had this curve at the beginning when I was looking at the convergence of linear stability, but it's also very useful to see what experiments do. Okay, so typically when they're putting power in, so they're driving the temperature gradient across here. Okay, they can do that very well, but typically experiments are descending, into, so this purple region here, I call it, this is the low Rossby number regime. They're kind of descending into it in this fashion, and this is really hard for them. So as they come, when you're talking about, Rayleigh numbers 10 to the 12, 10 to the 13, they're not really experiencing a lot of this regime. We live over here, okay, in this thing. We can keep going with the asymptotic model, but it's very hard for them to, it's very hard for them to enter this regime and get enough of a range in order to get enough of a range to see the full range of morphology. So one of the things they want to do is get into the geostrophic turbulence regime, which is sort of up here, and they have a hard time doing that. But guided with some of the solutions that we have, they can interpret what they're seeing. So here's some here are some tank renditions from John Arnaud's group where they're going through at various Ekman numbers, and they could, so they can claim to see some of the flow morphologies. You can see the impacts of rotation on those things. But here's the hard thing, so one of the things the experimentalists do very well is measure heat transport, the Nusselt number. Okay, and as I said, typically they fix the rotation rate, and they try to descend into this regime. Okay, by lowering the heat input into the fluid, and it's incredibly hard in terms of what they lack in this thing is the thermal control on the experiments. As they're coming down from the high end, okay, not going the other way, they lack the ability. They lose heat out of side walls and things, so they lack actually thermal control to actually get down on onto the geostrophic branch. So typically what they have done, and in this graph but from John Arnaud, they've reverted to DNS experiments to try to tell them what's going on in the lower branch here. And Of course, they're interested, Nusselt number, and the scaling of it is maybe a proxy for flow transition, and it's also a proxy if you're trying to extrapolate out to GFD objects. So kind of knowing the exponents, you can see here, there's some classical ones. You can see this black line is sort of the non-rotating branch, where we know from theory that the Nusselt number scales to the 1/3 power. And you can see here that in all of these, of course, rotation it's lower in terms of the heat output because it's below that in terms of Nusselt number, but it has a propensity to have larger exponents. So it's by exponent is sort of more efficient in terms of what it's carrying, but by actual absolute Nusselt number, it's not as efficient. And of course, this sort of is a story here. Why are they running these lab experiments? They're doing them down here, and they're trying to get out to or extrapolate out, and where are you in this diagram matters. What kind of your scaling exponent you have, or how you're shooting. These all matter. Yeah. So they're interested from that point of view. Okay. And I said, if I extrapolate it, we kind of designed the model that kind of lives out here. Yeah. So that's why there's interest. There's been interest in this. But it's not just us telling them what's happening. We have to interact, and there's some synergy there. So let's just just 5 minutes. Maybe I can briefly talk about go through this. So this is one of the things they're interested in. This is measured very well-ish. I will say again, depending on how low they can get down. But if you include DNS, they're doing a pretty good job in measuring a Nusselt number. And the idea is try to figure out, a scaling law for the heat, the heat flux going through the fluid. How does it depend on the Prandtl number scaling, more importantly, the Rayleigh number scaling, and rotation rates, or the Ekman number. Yeah. So this has been done for the non-rotating case. So the non-rotating case you may hear. So I've got some names here. Non-rotating case, you can have on the back of the envelope kind of derive some scaling laws. So you can have a scaling law where the heat flux is independent of depth, so the boundary independent of depth, so it doesn't really know about those. If you do that, you'll get the 1/3 scaling for non-rotating convection. If you forget about, X this out, no rotation, and you try to look at when H is independent here, you can see alpha will be 1/3 to cancel out the height. You can do the same thing with the dissipation parameters. Here, so to see when this has an ideal, law where the heat flux doesn't depend on molecular properties, and in a non-rotating case, you get a half. Okay, and there's been a lot, of course, that community has been really searching to see whether you can, drive that fluid into a turbulent scaling law of 1/2. Okay, let's just think about this from the point of view of rotation. What does it say? Yeah, so normally when you're doing this, so I should say here, I think I had it on the previous. Did I have it on the previous slide? Yeah, so on the previous slide, we're really looking at the Nusselt number. It turns out the important thing is how supercritical you are. So in this case, you've got a critical Rayleigh number on the bottom. In non-rotating case, that's a constant. In rotation, it's not a constant. So when you go through similar arguments, okay, which have been forwarded or put forth by these people here. If you're looking at the case where you are either depth independence on the scaling law, or even the boundary layer is marginally unstable, you'll pick up an exponent of 3. Okay, so that's the efficiency of the heat transport here. If you go to a turbulent scaling, you pick up a transport things of 3/2. Okay, and my point here is that this is opposite to non-rotating. So non-rotating, you would have 1/3 here, and you have 1/2 here. 1/3 is less than 1/2, so it tells you that boundary layers are the thing that is throttling the flux into the fluid. It's the reverse here. okay? When you do this scaling, it's not the boundary layers, it's actually the turbulent interior that is in fact throttling the flux. That's what's controlling the heat flux through that, but it's still an ideal scaling law. So this has, we should see this in the fluid when we actually, this is easier to get, there's no boundary layer control, and we do, okay? So if we go through that and you run the simulations and you compute the Nusselt numbers, we actually indeed see, we get this dissipation-free scaling law. Okay, so as I said, it's the thermal interior that is the flux, and you can do this by, there's just like the Navier-Stokes equations or the convection equations. There's some exact power integrals, and that you can actually divvy up the Nusselt number based on contributions from the interior and the boundary, and you can actually show it is indeed the interior that is dominating the heat flux that's going through the problem. We see this in DNS. I've got a few minutes, hopefully just gone over just probably a couple of minutes here. You see that in DNS, but you can also see it, you can also begin to see this. These are hydrodynamic Rayleigh-Bernard experiments being done in the sphere by Gastine, and you can also see evidence of this scaling law in the sphere as well. Okay, so as you're lowering the Ekman number, as he lowers the Ekman number, which is going that way, he's, this compensation line shows that he's actually seeing this in the fluid. Okay, I'll do make one more comment here. The large-scale vortex does complicate things, okay? But having it there, actually, we found by sort of going to very large reduced Rayleigh numbers does impact the scaling law. It actually tends to put more heat into the fluid. And so it doesn't really follow this law. So large scale features do impact the flow, but we're able to show that, if we're able to shut it off, which we do. So what we do in a simulation, we shut off the depth average, or subtract it every time step and just let the convection boil a small scale convection. So we shut off the inverse cascade, and in this compensated law here, we see we retain this idle law. So it's time. I'll just say it's in the notes, but there is a small story here that, between when the experimentalists actually were looking at what heat transport scaling exponents they saw, we got this bizarre thing. This was by John Arno and his group, that as they lowered the Ekman number, they weren't going to 3/2, they're going the other way, and I would say, I told them you should lower the Ekman number, and you see a tendency, you should see, so in this graph is the exponent, they're going up. And here's where the asymptotic says you should be if you're geostrophic turbulence, or if you're in a convective Taylor column regime, and they've just blown through that. Yeah, so something's going on, and I didn't get to that, but it's in the notes. The story is Ekman pumping. Yeah, so in the labs you can actually see that Ekman pumping is able to drive a response to the heat transport very close to the layer. So we get very good at, we can, well, let's go to this prior one. This was shown by Stefan in a paper that I was involved with, where we did a simulation where we, switched on the pumping. Okay, well, no slip boundary, I said this, but we did a simulation with no slip boundary conditions, and we did one with the pumping boundary conditions that I talked about last lecture. And you can see that you get the identical response in terms of the heat transport in this Nusselt-Rayleigh scaling. So it is pumping that is doing that. We can capture that in the reduced model and compare it with the DNS. We get excellent agreement there. There's a story why, I don't think I have time, maybe you can talk about that if you want later, but it's in the notes. There's a story why the exponent actually is increasing in the experiments. It's really, they're not in the geostrophic turbulence regime. They're actually more in this convective Taylor column regime. And we can actually revert to looking at single mode solutions, and we can actually, by some analysis, talk about when there's a threshold when Ekman pumping switches on, okay? And the heat transport gets enhanced. And they're just really looking at that transitional regime as, you know, in steep before it saturates again. They're sitting in there, and that's essentially why they're seeing the large scale, this heat exponent becoming large. But I'm going to stop there because that's will take a bit of time. So, okay, thank you.
So I was just curious, so you have transitions between them. Do you understand those phase transitions? That there's some kind of, it seems like there's some long range order that like the effective Taylor problem, you have some correlation between the top and the bottom of that gets killed and going to the food.
In a sense, yes, you'll see that. I mean, you can see, if you look closely, you can kind of see those signatures. You can see those signatures even in the Nusselt number. Yeah. So if you're looking at what will happen, you can actually see breaks, you know, of in the Nusselt number, which would be, you know, looking at, you know, sort of phase transitions or first order phase transitions where something, you know, it's not gradual, something happens in the fluid. Certainly between the cells and convective columns, it's a first order, yeah. The convective Taylor columns to plumes probably is a little softer in terms of what, you know, when you look at the dynamics, I would think, okay. Yes.
Question about the hexagonal pattern beginning of the reaction. It seems that the updraft and downdraft are not of the same sequence, but for the time when the updraft and downdraft are symmetric.
Oh no, they are here. I mean, when I did this, the hexagons, they're same. You know, if you're looking at, there's no symmetry breaking in this, you know, this problem. I've got, you know, symmetric. The boundary conditions are symmetric. So if you have an up hexagon, there's a down hexagon. You know, I can flip it and get the same thing. Yeah. So yeah. So typically, when you see that breaking between up and down, you've broken something. You know, either the fluid becomes non-Boussonesque, or your boundary conditions have become asymmetric, you know, like Marangoni convection. When you're seeing really Bernard, you've got, you know, it's driven differently, but, you know, top boundaries behaving, you know, you've broken a symmetry, and then it's, you know, the degeneracy between up and down is broken.